Hello, this is Miraj Patel, and today we're going to be finishing up Unit 6, which is all about covalent bonding, and today we're going to briefly talk about how to name compounds, and then we're going to do a quick brief review of everything. And so here we have a statement, so carbon and oxygen combine to form carbon monoxide and carbon dioxide, but these two invisible gases are very different. And so carbon monoxide is just impartial burning. So if we have, and it's also toxic, so that's why, gases from fumes, which is mostly carbon monoxide, is deadly. But carbon dioxide isn't really poisonous. All it does is, we just can't breathe it, so that's why we have to exhale it. But carbon monoxide is totally different. And the only difference pretty much is the little prefix, and we'll talk more about how to name covalently bonded uh, molecules. And so a prefix tells how many of each atom, how many atoms of each element there are in one molecule. And so here's a list of the prefixes. I'm sure most of you have heard of them, like mono, which is 1, di 2, tri 3, tetra is 4. That's tri is how we get trigonal pyramidal and trigonal planar because we have 3 atoms bonded. Then we have tetra, which is 4. Same thing with the going back to the atomic structure. Tetrahedrals are 4 atoms bonded to one central. Then we have penta, which is 5. Hexa, 6, like a hexagon. Hepta, 7, like a heptagon. Octa, 8, octagon again. Nona is 9, so like a nonagon, and then deca is 10, like a decagon. So these might be familiar to you from geometry class. So if you know this, like octagon, triangle, pentagon, heptagon, hexagon, you would be pretty good at just remembering this. So it's the same exact thing. And so here, bring it back to the example. Carbon monoxide, this prefix tells you the number of oxygen. And so there's 1 oxygen, carbon monoxide, and 2 in carbon dioxide. So if you look at our prefixes, mono is 1 and di is 2. So that's what the difference. And so here are the 4 rules we need to know how to name molecules. So first we name the elements in formula order. So if it's N2O, we do nitrogen and oxygen in order. Then prefixes show the number of each atom. So it would be, in this example, di means 2, so we have 2 nitrogen, so we put di in front of nitrogen, and mono but in front of oxygen. And then we had suffixes, so "ide", so we added to the last element. So instead of monooxygen, it's monooxide instead. And the 4th rule is no prefix mono for the first element. So let's go ahead and name these elements. So here we have carbon, so and chlorine. And so we first named the elements in the formula order, so we put carbon and chlorine. Then we had prefixes to show the number of atoms, so we had monocarbon tetra for 4 and chlorine. And then we add ide, so it's right now it'll be monocarbon tetrachloride. And then it says no prefixes for mono for the first element, so it'll be just carbon tetrachloride as your final name. Same thing with S. So now that we know mono can't be the first one, we can just go ahead and ignore mono for the first one. So we have sulfur, then we have oxygen. We don't add mono to the first one, but we add tri to the second element, and so we have oxygen here. So it will be trioxygen, and then we add IDE because it's the last element. So it'll be sulfur trioxide. Then we have H2O, and so we first add the 2 elements in order, and we have hydrogen and oxygen. So it's dihydrogen because there's 2 hydrogen, and then monooxygen, but then we add IDE because it's the last element. So it's dihydrogen monoxide. And so here's a quick quiz to see what you learned. So which of the following compounds is named incorrectly? Carbon disulfide, boron tetrachloride, iodine heptafluoride, or phosphorus hexachloride. So let's go through each name and match it with its see if it's correct. So we have carbon disulfide. So carbon. So there's a understood mono in front. Um, and so the only time we have just the name in front is because if it's mono. And so it is mono in this. And then we have two sulfur, so it's disulfide. And it does have its IED like normal, and it has a di for 2. Then we have boron trichloride. So we have one boron, which is good, because again, there's a assumed mono here. And then we have tri for 3, so there are 3 chlorine. And then chloride, ide is the correct ending. And then we have iodine heptafluoride, so iodine is good. Again, understood mono, which is 1 iodine. Then we have hepta for 7, and fluoride. And the IDE is correct, and it has the correct element. So phosphorus, and then let's just see what's wrong with this. So phosphorus hexachloride. So phosphorus is correct because there's one phosphorus here. Then we have chlorine, but we have 5 here, and this one says we have 6. So this one's incorrectly named because of this little prefix. It should be pentachloride. So then question 2, which of the following molecular compounds is named incorrectly? And so pretty much it's the same exact thing, but a different set. So here we have phosphorus trichloride. So let's just by the way go through each answer. So phosphorus trichloride is phosphorus is correct because there's one phosphorus. Tri is correct because there's 3. And then chloride is correct because it has the correct ending and correct element. So this one's correct. Then dicarbon pentaoxide. So pentaoxide. And di is correct, so carbon. And then we have pentoxide. So penta is 5. And then oxide is correct because it's oxygen. And then we have carbon tetrafluoride. So carbon's correct because we have assumed mono here. Tetra is 4. And then fluoride is also correct because it's fluorine and it has an IDE ending. And then we have hydrogen monophosphide. And so this one's incorrect because we need 3 hydrogens, so it should be trihydrogen monophosphide. So that is the incorrect one. And so number 3, the correct formula for hexaphosphorus trisulfide is A, P7S3, B, S3P6, C, P6S3, or D, S3P7. So we have hexaphosphorus trisulfide. So if you remember the rules, the name should be in the exact same order as the formula. So phosphorus needs to be first, and then sulfur. And if you remember, hexa is 6, just like hexagon. So, just like a hexagon. So it should be P6S3. So if you the correct answer is C. And here's a quick review of the prefixes again. So mono is 1, di is 2. So think of like dissecting an angle. So like we cut an angle in half, and then mono, think of like monorail, so like a train with 1 rail. Tri is for like triangle, so 3 edges. Tetra is 4, just like Tetris, which is all about 4 blocks. Penta is 5, so just think about a pentagon. Then again, hexa, hepta, octa, nona, and deca. Just think of the hexagon, heptagon, octagon, nonagon, decagon, and they have 6, 7, 8, 9, 10 sides respectively. And here now we're gonna do a quick review of covalent bonds in general. So we're going back to just drawing the Lewis dot structures. And so pretty much covalent bonding is all about getting 8 electrons, which is called the octet rule. And when you're drawing Lewis dot structures, we first keep a track of all the valence electrons. So here we have 5 valence electrons from phosphorus, 7 from each of the chlorines, but times 3 because we have 3 of them. So we have total of 26. Then we put the least electronegative in the middle. Then we connect them all. And as we do this, we have to keep track of the electrons. So we used up 6, 2 from each. Then we fill outer octets first. So we take all these remaining electrons and fill up the outer octets. And then we take the remainder and use it to fill up the central atom's octet. And so this works out perfectly for phosphorus trichloride, which now you know from naming covalently molecular compounds. And so those are the 1 through 4 steps. And so here's another example. So if you, same thing, so we have hydrogen, carbon, nitrogen. So if you run out of electrons before the central atom has octet, we have to start making double bonds and triple bonds until this one's satisfied. So we just take electrons from the one with extra electrons. And so here we took these 2 electrons from nitrogen and formed a double bond, but that still didn't work because it only has 6 electrons. So then we took another pair and used it for a bond and formed a triple bond. And so then we move on to the VSEPR diagrams and molecular geometry. And so valence shell electron pair repulsion theory, or VSEPR, is the theory that electrons spread out in different shapes to minimize repulsions, and that's what causes these shapes. So here we talk about electron domains. So all single or double or triple bonds count as one electron domain. So this is one domain, one domain, one domain, and then each lone pair counts as one domain too. So here we have 1, 2, 3, 4 domains, 3 bonds, which each count as one, then one lone pair. And again, we just answer this question. And so 1, 2, 3, and then 4. So when we write the electron domain like a little formula, A is the central atom, B is the number of bonds, so we have 3 bonds in this case, and E is the number of lone pairs, so we have 1. So we write A, B, 3, because 3 bonds, and then E. And 3 atoms and 1 lone pair. And then here, this is how, these are all 5 types of shapes. So we have the first one, which is 1 central atom, 2 bonds, so 2 domains, and then this is a linear shape with bond angle of 180 degrees, just like a line. An example of this is CO2, and see how it forms a straight line. Then we have the second one, which is AB3, so 1 central atom, 3 bonds, and total of 3 domains, and the shape is called trigonal planar. Tri for 3, planar for it's on the same plane, like in geometry. Then the bond angle is 120, so just think about a circle, and we split up into 3 sections, 120 each little distance gap. And an example of this in real life is boron trifluoride. And then we have these 3 other shapes. The first one is tetra, or tetrahedral. Tetra for 4, because there's 4 molecules, or 4 atoms bonded to a central atom. And the bond angle is weird. It's not 90 degrees like you would think so, but it's 109.5. And that's the angle from this top arm to the side ones. And then an example is CH4. So carbon tetrahydride. And then we have NH3, which is an example of the third shape, which has 1 central atom, 3 bonds, and 1 lone pair, which is represented by the E. and it's called trigonal pyramidal. So tri for 3 atoms bonded to a central, pyramidal for like a pyramid. And it's because of this lone pair that all these atoms are pushed down, which causes the pyramid shape. And then we have AB2E2, so one central atom, 2 bonds, and then 2 lone pairs that are floating outside that push them down. And this is called a bent shaped because it forms like a bent like line. And a good example is H2O or water. And then, so pretty much the way you predict them is first we have to draw the Lewis dot structure, which we learned about in the first video of covalent bonding. And then after we draw the Lewis structure, we have to count the electron domains and get that little formula. So A is the middle one, and then B is the number of bonds, and E is the number of electrons. So we have to count, but here it's not AB4, but it's AB3E, because there's 1, 2, 3, 3 bonds and 1 lone pair. And then after we get this little formula, we can go back and to all these shapes and see which shape it is. And so if it's AB3E, it's trigonal pyramidal because that one lone pair pushes all these atoms down. And so that is how we get the shape, trigonal pyramidal. And now we're just going to briefly touch polar versus nonpolar bonds. And so pretty much we have the bonding, which is split into ionic, covalent. Ionic is what we talked about the last unit, which is between metals and nonmetals, and the electrons are hogged by one or the other. It's never shared. But covalent, electrons are shared. They can be shared equally, which is nonpolar, or they can be shared unequally, which is like polar. And so pretty much polar means like just like how the Earth has 2 poles, one slightly positive, one slightly negative. This is what exactly happens in atoms. So one side becomes slightly negative and positive, forming poles. And so this is like a good analogy of a nonpolar bond. Nonpolar bonds, the electrons are pulled equally, just like in this scenario with the tug of war. Both sides are pulling equally, so the central electron here does not move to either side, so it just stays in the middle. And so here's the definition. So atoms with equal pull, so similar electronegativity, so it means they pull similarly on unbonded electrons or whatever. So they pull with similar force, so bonding electrons are shared equally. So the electrons pretty much just stay in the middle. They don't go to one side nor the other. Good examples of this is diatomic elements, because if we have 2 hydrogens and each hydrogen pulls with the same force and they're pulling on each other, neither side can overtake the other because they're exactly the same. And then we have polar covalent, which are the exact opposite. So bonding electrons are shared unequally. So this happens when you have a very electronegative element like chlorine or fluorine take electrons from like a weaker element, so like hydrogen. And so pretty much the more electronegative side pulls the electrons towards it, making it slightly negative, and the other side slightly positive. So this means partial, so if you see this and plus, it means partially positive, and then this with the negative is partially negative. And then this forms a dipole, or molecules with 2 poles, slightly positive and slightly negative. And then here's a chart. So pretty much based off of the difference in electronegativity, you can tell whether it's nonpolar, moderately polar, very polar, or ionic. And so basically you just subtract the 2 different electronegativities like this, and you get this number, and you see where it fits in this range or this scale, and you find the corresponding category. And just FYI, fluorine is the most electronegative, and it has an electronegativity of 4, and everything else is lower. So if you subtract difference of 2 different elements that are bonded, you can tell whether it's polar, nonpolar, or very polar, or ionic. And so pretty much here's the summary. Ionic electrons are transferred between one or the other. Polar covalent, electrons are shared unequally like this, but the smaller side still gets some of the electrons. Then we have nonpolar covalent, which the electrons are shared equally. And pretty much polar molecules have polar bonds, and it's arranged asymmetrically, so pretty much these bonds don't cancel out. So for example, if we had polar bonds like this, uh, and they were pulling one to the left and one to the right, and they were both the same force, they would cancel out and form a non-polar thing. So it's important, that shape. So it's important that these bonds do not cancel out each other. But in this case, the bonds are going one direction this way and one direction this way. And so they do not cancel each other out. But if this bond was going this way and one was going this way for some reason, then they would cancel out and there would be no bond. So, I mean, no polarity. So the shape does matter. And so here's some examples of polar molecules like water, which is this right here, hydrochloric acid, carbon trihydride, and then with chlorine, and then we have ammonia. And so here's some examples. See how the dipole pulls it towards a more electronegative atom, and there's no bonds canceling them out. But then if we have nonpolar molecules, or atoms with molecules with no polar bonds, it's definitely nonpolar, or it has polar bonds that cancel out. So here is a good example, CO2. So these two polar bonds, because they go opposite directions, they cancel out, and there's no net movement of electrons. So it's actually nonpolar even though it has polar bonds. And so it's also important to know that shape matters. Or you can have molecules that have no polar bonds, like two chlorines pulling on each other. So if you see a diatomic element, know that it's nonpolar. Or if it has polar bonds like this, but they cancel each other out, then it's nonpolar also. And so here's some more elements. So notice how all these polar bonds, even though they're polar, they're canceling each other out because one goes this way, one goes this way, and one goes this way. In total, or net force, there's no electron movement. And same thing with this one. One goes up, one goes down, one goes to the right, and one goes to the left. So there's no electron movement. And that is it for today. So in summary, we just talked about covalent bonds and how to name them, and we talked about all the prefixes, and just remember those 4 rules: how to name electrons and name molecular compounds. And then we have to know how to do Lewis dot structures, so counting the electrons, making sure you bond them, and making sure they have octets. And then based off of that knowledge, you can learn VSEPR models, which are how the electrons behave and how the shape of the actual molecule looks. And there's like 5 different shapes: linear, bent, tetrahedral, trigonal planar, and trigonal pyramidal. And so that's all based off of the Lewis dot structures. And based off of those Lewis dot structures and all what you learned, you can figure out whether they're polar or nonpolar based off of if they're sharing them not equally, which is polar, and equally, which is nonpolar. And so I hope that helped you get a quick review of covalent bonding. If you need more detailed explanations, please refer back to the videos that describe about them respectively. And so the next unit is going to be all about percent composition and chemical composition of different compounds. And so we'll see you later, and hope you have a good day.